Okay. Okay. Let me wait for a few minutes to start the session, and then we'll start this week's tutorial session. Present my okay. Okay. So let's just wait for few minutes to others to join, and then we can start our session. Let me check. Let me check whether this session is being recorded or not. Yeah, it's being recorded. Looks like this is the festive season, so most of you guys probably will not join today. Okay, just wait for a few minutes. Okay, we'll start. So, welcome everyone for today's session. This is the fifth assignment session, and today we will discuss the assignments based on the lectures of week 5. And for this course, basic thermodynamics, classical and statistical approaches. I am Dibyendu, as you all know, and let's just begin the session. Just if you want to know about my research work, if you want to know if you want to know about the current research topic that I'm working on, you can visit my website and you can find all the informations there, and you can also connect with me regarding any discussions or any kind of discussions. And this is the YouTube channel where I will post all the video contents. And also, I think you guys are being informed about the weekly update of these sessions, probably in your course information tabs. So there in the NPTEL, there is a in my channel there will be a folder, or there will be a dedicated playlist. There I am putting all those video lectures, so you can find it, and probably the title of all those videos is starting from like the week number, so you can sort those things out. Okay, so okay, so before going into the assignment session, I want to just repeat few things that so far what have we studied. We have studied about basic thermodynamic processes, and we have studied about the zeroth law of thermodynamics. What are the main essences that zeroth law of thermodynamics talks about, and then we we enlarged our idea, and we get the energy conservations or first law of thermodynamics, and later we dive deeper, and we found the second law of thermodynamics, and there are different kind of versions of different versions of second law of thermodynamics. There will be Clausius statement, there Kelvin Planck statement, so different kind of versions of second law of thermodynamics. And there we have got to know one interesting concept, which is entropy, and we have tried to define what is entropy. There are multiple definitions of entropy. So far we have just approached entropy from thermodynamic perspective. There are different other entropy also. There are namely configurational entropy, different kind of entropy you can find, because this and the concept of entropy is everywhere. You can find it in computer science, you can find it in mathematics, probability, everywhere. So this is a central theme to understand. And then we have actually studied about different Maxwell relations. So what those Maxwell relations do, they actually relate between different free energies and different thermodynamic variables. So there are different free energies, like Helmholtz free energy, Gibbs free energy, enthalpy, and also like the thermodynamic variables like pressure, volume, temperature. So we can connect to those free energies with respect to the thermodynamic variables, entropy, temperature, pressure, volume, and all those things. And sort of we later got to know about thermodynamic engine, the Carnot engine, and what are the efficiency regarding that, ideal refrigerator, and all those stuff. Today's lecture actually the extension of those ideas. Today the assignments will be on those things, and those things are ideal heat engine and also like reversible, irreversible processes, because these things are quite tough to these concepts are quite tough to grasp. So you have to pay more attention to understand, because here there are not much mathematics, rather than much more physical or hand waving arguments to connect those ideas. So just pay attention to those things, and I hope you will get to understand all those things quite easily. Without a further ado, let's start the session. Okay. So the first question says the process involved in ideal Stirling engine are: first option is isothermal compression, isochoric heat addition, isothermal expansion, isochoric heat removal. Okay, that sounds good. Second option is irreversible isothermal expansion. Okay, adiabatic expansion. Okay, reversible isothermal compression, adiabatic compression. The third option says isochoric heat addition, adiabatic expansion, isochoric heat removal, and adiabatic compression. So the third options probably you just know. Okay, so these third options, this option, this is Carnot engine, right? This is pretty straightforward. This is Carnot engine. So Carnot engine, we know that there is isothermals, and then this is Carnot engine. So this cannot be something. Okay, and let's just first know this first thing, reversible isothermal expansion. So this reversible thing is means this is not something that we have to worry about, because everything, this process is the ideal Stirling engine, all the processes are reversible. But isothermal expansion, then adiabatic expansion, and then again isothermal compression, adiabatic compression, this is also like Carnot's engine, sort of a Carnot's engine, but like in that same spirit. Okay, so the first option, so it looks like we are left with only this last option, but let's just draw the diagram. So the PV diagram of ideal Stirling engine. Okay, so the PV diagram is okay. So it looks like this. Okay, this is P, this is P. These are so if there are isothermal compression, this is the isotherms, these are isotherms. It can be more steep, but these are straight lines. This is isochoric because V is fixed. First is isothermal compression, means V decreases. Then isochoric heat addition, so there will be some heat addition because P is changing. Then isothermal expansion, okay. Then isochoric heat removal. Okay, so this is ideal Stirling engine. So just name these things A, B, C, D. Process A, B is, so for the process A, B, P and V both are changing. P, V both changes. Okay, so and also this is isothermal. T, constant, and it is isothermal, and V actually decreases. So this is isothermal compression. Okay. Then again there is a process, second process is BC. So V doesn't change, V does not change. So this is isochoric, right? But heat addition, how can you say that? Because this is this temperature of this and temperature of this isotherms, which, so from these things how can you tell that which has higher temperature? Obviously this one, right? Because as temperature increases, the isotherms tends to go higher and higher, because there will be PV and RT. So T increases, the times of P and V, that will also increase. So this is, if this is T1 and if this is T2, so according to these isotherms, T1 greater than T2. So this will be isochoric heat addition. Now third process is process CD. In CD also the same, but here temperature is fixed, so this is isothermal. Now V increases, so this is isothermal expansion, right? Process, last process is process DA. Here also like the V doesn't change, so this is isochoric. But here, since the isotherms is lower, because we are changing from D to A and we are touching lower isotherm, so this is isothermal heat reduction or heat removal. These are the 4 steps of ideal heat engine. Okay. There are also different types of Stirling engine. Okay, and they are classified like alpha, beta, gamma, this kind of Stirling it is. Okay. So there are alpha, beta, gamma, Stirling engine. In recent times, these are quite recent, means like I am talking about 5 to 6 years ago. So actually I am also working with that some system that is called active matter, means bacterial bath. So this bacterial bath is different from the thermal bath. So this has some activity, and we actually assign some effective temperature to the bath, and we actually in recent times also this kind of active heat engine also being realized using different systems. So here the system is not thermal because no thermal work, but or means like the depending on the temperature, the whole system is not governed. There is also activity. So we are also like going back. We are taking some clues from the history, and we are trying to implement if we want to get some newer kind of heat engine. And interestingly, 1 or 2 3 new papers have been reported, and they actually claimed that we are getting more efficiency than like the heat engine. The active heat engine is giving more efficiency than thermal heat engine. So this is quite interesting. So if you guys want to know about or more, because this is quite advanced topics, so you can actually there is a paper in Nature Physics by professors AK Sood's group. So you can follow that paper, or you can get some idea about it. Sorry, in the next class, if I remember, I will give you the link or ID, because I haven't taken, or I haven't had this information right now with me. Okay, so that's it. Okay, so just okay, let me go to the next problem. Next problem is quite straightforward, because you all know about Carnot engine from your school days, from 12, and then so probably you guys know about those things. So second question says, in the entropy versus temperature graph of Carnot cycle given below, which step represents reversible adiabatic compression? It is quite easy. Let's just solve it step by step. Okay, so here the trick is that you guys actually have seen the PV diagram about the ideal Carnot cycle. So they have just given TS diagram. Okay, let me mark it. So this will be this option, right? It's quite straightforward. Okay, so we'll do from scratch. Okay, so we know about PV diagram. Let me just show PV diagram. Let me first give the axis level. So there is some like these two isotherms. Okay, just one-to-one correspondence. Let's check. Okay, one-to-one correspondence. Okay, so there are 4 processes: adiabatic expansion, at first adiabatic expansion, then isothermal compression, then adiabatic isothermal compression, then adiabatic compression, and then again isothermal expansion. And for adiabatic process, you know that change in entropy is 0, because these are all reversible processes. So for, let me write for this, for reversible adiabatic process, delta S equal to 0. So S equal to constant. So let's just identify where S is constant. So this C and DC and AB, these two processes are entropy is constant. So C and CD and AB, these two graphs, these two processes, this one and this one. But which one is which? That we have to identify. Now, which has lower temperature. That can be one graph, because this graph, this curve, isothermal curve, is of higher temperature. This is T1 and this is T2, and T1 greater than T2. So here T1 is this one and T2 is this one. So T1 is greater, T2 is. So in that graph, A and D actually A and D so this will be A and D, they are in one isotherm. So this is AD. If we get AD, then this is C, obviously, no other chance, because DC was one process and this is B. Okay, because so this is one thing, this is one, so these are the processes. Okay, let me just go to the corresponding. So 1. So isothermal expansion what is the question actually? Reversible adiabatic compression. Reversible adiabatic compression. So compression means the volume decreases. Let's just take isothermal expansion of this BC. So this is BC, CB. Sorry, CB is expansion, okay. But this is at T2 temperature. And isothermal compression this is AD at T1 temperature. Adiabatic compression. Now here in this process V is increasing. So in this will be the process. So DC and adiabatic expansion will be this one. Sorry, this will be adiabatic expansion because V is increasing. Sorry, adiabatic expansion. And this will be adiabatic compression. This is BA. What was the question? Question was okay. Sorry for the okay. Okay, here question was which is reversible adiabatic compression. So that will be B. Okay, straightforward. This is B. Okay. Just look at this problem. Once, and let me know if you have any problem. Okay. Next, going to the next problem. This problem says a Carnot engine converts 1/8 of heat input into work. 1/8 of heat input into work. So from the hot reservoir, the amount of heat, that is QH, so that he put into work the 1/8 of QH. Okay. So when temperature of the sink is reduced by 50 degrees centigrade, its efficiency is doubled. Okay, good. Find the temperature of the cold sink and the hot source. Okay. Okay. So there are enough hints. So first thing first, as you know, the efficiency eta is 1 minus Tc by Th. It goes Th minus Tc by Th, and that is W by QH, and that is 1 by 8. One relation we actually get. Okay. So if we add so Tc by Th, actually Tc by Th will be Tc by Th will be, you go this way, if it is come this way, and Tc by Th this way, there is 7 by 8, and it becomes that. Okay. Now the question says that when the temperature of the sink is reduced, sink means cold, 50 degree centigrade, its efficiency is doubled. Okay, good. Means that will become eta prime is become 1 by 4. So in that new thing, that eta prime is 1 minus Tc prime by Th is 1/8 times 2, that is 1 by 4. And if you go this way, then Tc prime by Th becomes 3 by 4. So now Tc prime is Tc minus 50. Now 50 degree by reduced by 50 degree centigrade is same as 50 degree Kelvin, right? Because just scaling and adding 273 will be the same thing. Okay. Okay. So then Tc minus 50 by, anyone wants to join? Tc minus 50 by Th is equal to 3 by 4. And also we know Tc by Th, that is 7 by 8, minus 50 by Th. So this is relation number 1, this is relation number 2, this is relation number 3. Okay, so this is 3 by 4. So 50 by Th, that is 7 by 8 minus 3 by 4, that becomes 1 by 8, and which becomes Th as 400 Kelvin. Okay, so now if its Th is 400 Kelvin, Tc should be 7 by 8 into Th, and that produces 350 Kelvin. Okay, so this is the correct option. Cold sink, this is the correct option. Okay, so pretty simple problem. So what have we done? We actually first calculated the efficiency, and its formula is 1 minus Tc, that is 1 minus temperature of cold reservoir or the sink divided by temperature of hot reservoir or the source. And after doing the algebraic manipulation, also we got to know the one other definition of the efficiency is the delivered work of the heat engine, that is W divided by the heat extracted from the source, that is QH. And we know that extracted work is 1 by 8, 1/8 of heat extracted from the source. So 1 minus Tc by Th is equal to 1 by 8, and after the algebraic manipulation it becomes Tc by Th is 7 by 8. Now if we reduce the temperature by 50 degree centigrade, means 50 Kelvin, that eta prime, the new efficiency, will be 1 minus new temperature of the sink divided by temperature of the source. And after the same manipulation we got Tc prime, which is the new temperature of the sink, that Tc prime by Th is 3 by 4, and Tc prime is Tc minus 50, and after doing that we get Th is equal to 400 Kelvin, and after that Tc is equal to 350 Kelvin. No problem whatsoever. We just put some you just see this solution, and then we will go to the other problem. Okay, let's go to the other problem. Now this problem says that the graph of Carnot cycle for 1 mole of ideal gas is shown above, for which process delta U equal to 0. So the change in internal energy is 0. Now this is quite important information to know, that Carnot cycle. First thing is Carnot cycle. Carnot cycle. An ideal gas. So for ideal gas, U is U function of T only. So if delta U equal to 0, that means temperature constant. That is one only clue. That is the information you need. Now if you know this information, so this curve, this AD and BC, these are more stiffer. So these are the adiabatic processes. So AD and CB, these are adiabatic, more steeper, because you know that in the PV diagram, adiabatic processes are more steeper, and BA and DC, these are isothermal. These are isothermal process. Okay. Now, since we have to know that for which process del U equal to 0, so this is the isothermal processes for which in 0. This option will be and then DC. Okay, simple. Because since it is ideal gas and since there is internal energy change is solely and solemnly for temperature change, so delta equal to 0 means isothermal curves, because the temperature doesn't change. So this will be B and DC. Okay. Now the fifth problem. Fifth problem says fifth problem is quite interesting. Fifth problem says, what will be the change in entropy when 1 mole of an ideal gas is compressed to 1/4 of its initial volume and simultaneously heated to 4 times its initial temperature? So there are two information for so the change in entropy will be for two things. So what are the informations? So compressed, first thing is they are compressed to 1/4 of initial volume. So compressed means VF will be 1/4 of this one, and then also like heated 4 times to its initial temperature. So heated TF is equal to 4 Ti. Now since temperature changes, so U, there will be some delta U, and since volume changes, there will be some delta W. Now if you want to calculate the entropy, so for entropy for W, for work, is, what is that thing? That is P dV, that is work done, divided by T, because as we all know that this is the our equation, du is dq plus dw, and for reversible processes we can substitute this and we can write is tds plus dw is equal to du. Then we can write for exact differential ds du minus dw, and du is cv dt, so ds is cv dt by t, and dw is minus pv dv, so minus p dv by t. So it becomes delta s, we have to take the integral, so this will be ti to tf cv dt by t plus vi to vf p dv by t. Now, so delta s will be ti tf cv dt by t plus, now p is RT by V. So for ideal gas equation we know Pv is equal to nRT, so n is equal to 1, so this will be 1, so this is P is equal to RT by V. So RT will be cancel out, so this will be VA by VF, and this will be RT by V, so RT by VT by D. Now after doing the calculations we know this will be CV ln TF by TI plus R ln VF by VI. Now TF by TI is CV ln 4 plus R ln 1 by 4, because VF by VI is 1 by 4. So we can write CV minus R into ln for simple logarithm thing. So this option will be correct, option C. It is quite interesting, right? So whenever you just do that, you try to imagine things, what are the contribution to the entropy change, and if you know the contribution to the entropy change, you will just get the information about those things, and you will put those things together and you will get the whole picture. Okay, so let me repeat it for once so that you can follow it. So Vf, which is the final volume, is Vi by 4, and Tf is 4 Ti, means the initial temperatures 4 times. Now we know from first law of thermodynamics that du is equal to dq plus dw. Now for a reversible process, we can write the dq, the heat exchange, to as an exact functional, that is TdS. Then we can get TdS is equal to du minus dw, and then ds is equal to du, we know cv dt, so cv dt by t. Then minus of dw is minus pdv, so this minus and that minus cancel out, so this will be pdv by t. So the total entropy change for this process, delta S, will be cv dt by t, and that integral limit will be ti from tf plus p by t times dv, and we have to integrate it, and the integration limit will be vi to vf. Now we have to substitute the value of p according to ideal gas equations, and we have to write P is equal to RT by V, because we are talking about 1 mole of gas, that will be RT by V. Then we have to substitute that P into substitute the expression of P into that equation, then that will be RT by V, that TT cancel out, that will be R by V dV. Now after that, if you do the calculation, then there will be CV ln exponential base TF by TI plus R logarithm exponential base Vf by Vi. Since that is compression, so Vf is less than Vi, and how many times it is compressed, how much amount of volume is compressed, that is 1/4 of the initial volume. So Vf by Vi will be 1/4, and Tf by Ti will be 4. So that then just with some logarithmic change we can write Cv minus R, because ln of 1/4 is minus ln 4. So just see. Okay. Okay, since we have done 5 questions, I will give you some break, 5 or 6 minute break. Meanwhile, if you have any questions, you can ask me in the chat box, or we can take it after 5 to 6 minutes. Okay. Okay, welcome back. Okay, if you have any question, no question. So, Komi, let me go to the next problem. Now, in an adiabatic irreversible, the next question says, in an adiabatic irreversible expansion of an ideal gas, which of the following relation is true? Now, this is not, if it is adiabatic reversible, then what should be the case? Adiabatic reversible. So, the adiabatic reversible dq is 0 with surroundings, and also like then the delta system will be 0, delta S surrounding will be 0, and delta S universe will be 0. But here for irreversible process we cannot write like this. Now the logic behind this, we will construct it using two methods. Let's say I am going from point A to point B, okay, and this is irreversible. And also like in this process, let's say delta W, some work has been done in the infinitesimal part, okay. So where there will be some work delta W not equal to 0 in the infinitesimal path, okay. Now we know from the experience that this work would be different if the work coordinate were changing at different rate. So if this work coordinate occurs at different rate, the intrinsic friction will be different, obviously will be different, because the energy dissipation from the friction will be different, right? Now in the limit, when the process of infinite slowness, when this process infinite slowness an adiabatic process with the same initial state, with same initial state A and same change of work that is delta W if that would become reversible then the final state and final internal energy would differ from irreversible case, because there are in irreversible process we have to know the rate also, because that is depending on the rate also. Now that because of this final state with same work for reversible case will be different from B. Okay. Because there is no reversible adiabatic path with work between A to B, because there will not be any reversible path with same work between A to B. Because it is quite interesting, because here for reversible process all the states starting from A to B and all the intermediate states, everything needs to be equilibrium states. So let me add one paper. Okay, because another thing we have to, for reversible process all the states starting from A to B, including all the intermediate intermediate states have to be equilibrium states. Okay. Now, if any one of the states there will be difficulty to construct a reversible path connecting A to B with same work if any of the state is non-equilibrium. Okay, that is important, because if any of the states is non-equilibrium, how can we define the reversible path? In that case, we'll assume that one of the that state that is non-equilibrium has been replaced by a constrained equilibrium state with same entropy. So we will assume that state to be replaced by constrained equilibrium state with same entropy as for the non-equilibrium state. Okay, this thing up to this point it is clear. Okay, I will let you know what does these things mean. Okay, now if delta now if delta W equal to 0, no work done, then since this is delta Q equal to 0, then internal energy will be also 0. So here it is not possible, because delta Q is 0, delta W is 0, and delta U also 0. So a reversible limit cannot be reached. So cannot be reached. So we know from the above discussions, so there is no possibility of reversible path between A to B irrespective of work done only possibility if the path is non-adiabatic. Okay, so if the reversible path is non-adiabatic, we can construct a path. So from here we know, so then delta S A to B, as we know, we can construct a path where this is non-adiabatic, so this will be not equal to 0. Now not equal to 0 is proved. Whether it is positive or negative, that we have to justify from another angle. Let me add another page. So that can be actually discussed let's say there is one path that is A to B, which is irreversible, and now we are constructing a reversible path. So for this process, let's say suppose the system completes a cycle returning from B to A. Okay. Now from Clausius inequality we know this is delta S A to B, because that is the reverse only, so A to B minus of that, and that cannot be negative, because if this is negative, if delta is negative, then this minus of delta S AB will be positive. So delta S AB should be, cannot be, this is wrong, cannot be less than 0. So delta S AB should be greater than 0. So since it cannot be 0, cannot be negative, so only one option remains, that is delta S A to B greater than 0. In fact, this delta S irreversible is written as eta CV ln T1 by T2 or TB by TA plus NR ln VB by V. Okay. So this thing I want to repeat it again. So the Clausius inequality tells that in the case for B to A, and if we add the entropy for the infinitesimal path, that cannot be positive because the heat is flowing from cold to hot. Cannot be negative. Cannot be positive. So see this, since this is cannot be positive, this whole thing, then this cannot be negative. That's why this thing, and that is this one. So this is the whole picture. This is quite complicated. I hope it is clear. If it is not, let me just again reiterate the things again. Now, if the process would be adiabatic reversible, then delta Q equals 0 and all the system surrounding and universe, that is 0. Now, for irreversible process, we can think of two situations where one process is, some work is being done. If some work is being done in infinitesimal path, then in the limit of infinite slowness, an adiabatic process with same initial state A and the same change of work, that is delta W, would become reversible. And if that happens, then the final state and the final internal energy should be different, because in the irreversible path there is a change in, there is dissipation. Here in the reversible path there is no dissipation. If there is dissipation, we cannot get back the same thing again. Okay, so from that perspective, we cannot start from A with same work and reach to B via a reversible path. We have to, because since it dissipates, we need more energy, more work. Sorry, less work. Because in irreversible path there is always dissipation. So I am dissipating my energy to reach B, and in the reversible path there is no dissipation. So I would require less delta W, right? Less delta W. So in that heuristic approach, you can also see from this that delta Q is delta U minus delta W. So in the reversible path, delta W we need more compared to delta reversible. So to reach the same path, for reversible path, this difference will be more. Okay? Because to calculate the change in entropy from A to B, we need to construct a reversible path. And for that reversible path, to talk about the whole thing, we need less delta W, right? Then this difference will be more, one thing. And if delta W equal to 0, then delta Q is 0 because this is adiabatic. And then from the first law of thermodynamics, delta U also 0. So that reversible limit cannot be reached. So there is no possibility of reversible path between A to B, irrespective of work done, because in that process, that amount of work done is not possible for reversible case. So we can say that delta Q by delta TB is not 0 because delta Q is not 0. In the case, in irreversible path, there is no adiabatic reversible counterpart of that irreversible adiabatic counterpart. So there should be some delta Q. So that is should be greater or less than 0. Now, whether that is be positive or negative, that can be from Clausius statement. Because if we now construct a path from B to E, B to A, then that exchange of entropy will be minus delta S A to B, because entropy is a path function, state function that depends only of the state A and B. And we know from Clausius inequality that minus delta S A to B cannot be positive, because we are going from A to B and then coming back to B to A. So that cannot be positive. So that cannot be positive means minus delta S A to B cannot be positive means minus delta S A to B cannot be negative. And from that we can conclude that delta S A to B will be greater than 0. That's the thing. Okay. I hope you guys understood these things, because this is quite difficult to understand in this perspective. But from now on, you just remember these things. The delta S A to B for for adiabatic irreversible process is always greater than 0. Okay. Okay. Just see these things once and okay, let me go to the next problem. Now this problem says a heat engine operating between temperature 300 Kelvin and 500 Kelvin withdraws 2 kilojoule of heat from hot source. Then in a reversible process, how much heat it throws away to the cold sink? This is quite simple problem. You can do this problem very easily. Now, we know from this efficiency eta is 1 minus T cold by T hot divided by 1 minus Q heat extracted heat throw away to the cold sink, and heat ratio from heat throw away to the cold sink and heat extracted from the hot sink. And we can write also Tc by Th is Qc by QH. Now we know that Tc, Th 300 by 500, and Qc we have to calculate, and QH is 1.2 2 kilojoule. So this is 2 kilojoule. Okay, so QAC will be 2 times 3 by 5, 1.2 kilojoule. Okay, this is the answer. This is pretty simple. Okay, let me go to the next problem. This problem says, when two pieces of the same metal having same length but different temperatures, Th and Tc, are brought in thermal contact, then heat flows from hot piece to cold piece. That is pretty normal because heat flows from the hotter to colder region. And their temperature becomes same. Consider this temperature to be T. What will be the change for this process? Now this is quite simple. Okay. Now how can we do it? We already know how we have to do it. We have to do it like delta S is n CV dt T using, let me go to the expression before. So the expression was CV ln TF by TI plus R ln PF by PI. Now we will do some good thing. Okay. TI to TF plus VI to VF in R dV by V. Now if you get it, then LCV ln TF by TI plus NR ln VF by VI. Now you know VF by VI is TI PF and TF PI. PF, sorry, this will be PI. PI, sorry. So let me write it clearly. So PI VI by TI will be PF VF by TF. Now if we pressure is constant because there is no measurement in pressure, so P will be there. P is P. So there will be VF by VI will be TF by TI. Now if you write it, then it becomes NCV ln TF by TI plus NR ln TF by TI. Same thing. Okay, NCV plus R TF by TI, and that actually NCP ln TF by TI because CP is CV plus R. Okay, but here there are two things. One is hot, so TH to T and TC to T. Two things. Okay, so these whole expressions will be for two things. So then delta S will be delta S hot plus delta S cold. Okay, let me add one page and write it nice and clean. Okay, so then delta S will be delta S hot plus delta S cold, that will be N Cp ln. So delta L hot final temperature is T, right, and initial temperature was TF, and this delta S will be N Cp, final temperature is T, initial temperature is TC, sorry, TH TC, and if you combine them together in Cp, then it becomes T TH times T TC, then it becomes NCP ln T square by TH TC. Okay, so the option will be last option. Okay, let me go to the, this is a statement for an irreversible process, del Q reversible greater than 0. So just we have done this, del Q reversible by T greater than 0 always, because here as you know that delta Q, this delta U minus delta W, so delta reversible, always this thing is always greater than the delta U. Sorry, this difference will be always better than irreversible process. So this amount, so we have to construct a reversible path to formulate that. So if the difference is larger from the irreversible path and to go to the same thing, so that should be greater than 0. Okay. Now consider an isothermal expansion of an ideal gas into vacuum. This is an interesting problem. Sorry. Problem says, consider isothermal expansion of an ideal gas into vacuum. If this irreversible process entropy of the surroundings entropy is always unchanged, right, in irreversible process. So this will be quite statement kind of a thing. So it remains unchanged. So entropy of the surroundings remain okay. We will also visit some new problems. So before that, I want you to just see this problem and ask me from this thing, and that will be, I think, better. Okay, just ask from these two things. Okay, if you have no problem, then let me go to the other problems. Okay, so this problem says some heat engine A and a reversible heat engine B operate between same two heat reservoir. Okay, good. Now engine A has thermal efficiency equal to 2/3 of that reversible engine B. Which of the following sentence is right? Now this is pretty simple. This is theory. We always know that efficiency for reversible is always maximum. Since eta prime is less than eta reversible, so eta prime must be irreversible. So there should be, let me just check that. Okay. So there must be dissipation. Okay. So engine A is irreversible engine. Now plot TS diagram of below PV diagram. This is easy. We will just in the earlier problems we have done it. Okay. TS diagram. This is T. This is S. Now this 3 to 4 and 2 to 1, these are quite steeper. So these are adiabatic process. So adiabatic process means S is constant. So S is constant. And 2 to 3 and 1 to 4, 4 to 1, it's isothermal. So there should be constant T. Sorry, this would be a straight line. Now the process says, sorry, and this is now which is higher. So this 2 to 3 is at higher temperature. So 2 to 3 will be higher temperature. This is isothermal. So this should be higher temperature. And higher entropy means higher steeper, more steeper. So 4 or 1 will be in this lower temperature. That should be 4 and that should be 1. Sorry, this would be 4, this would be 1, and 2 or 3, this would be 2 and this would be 3. Now just write this 1 to 2, 1 to 2 and 2 to 3, then 3 to 4 and then 4 to 1. Okay, so let me write it. 2 to 3 and 4 to 1, these are isothermal, and 3 to 4 and 1 to 2, these are adiabatic. And since this is more higher, so it would be like this. Okay. Now this question says two identical bodies have internal energy U is equal to NCT with constant C. The values of N and C are the same for each body. The initial temperature of bodies are T1 and T2. They are used as a source of work by connecting them to a Carnot engine, bringing them to a common final temperature Tf. Okay, let me read it out. Two identical bodies have internal energy U is equal to nCt with constant C, means heat capacity. The values of N and C are the same for each body, means same material. The initial temperatures of the bodies are T1, T2, okay. They are used as a source, okay, source of work, okay. By connecting them to a Carnot heat engine and bringing them to a common final temperature Tf. What is the final temperature Tf and what is the work delivered? Okay. Now, as we know, this is Tf, this is T1, this is T2. Now, since efficiency is same, then 1 minus T2 by Tf by T and T1 and 1 minus T2 by Tf. Let's say I am taking T1 greater than T2 is like this. Then Tf by T1, so 1 T2 by Tf, that becomes Tf square is T1 T2, and that makes Tf T1 T2. Temperature cannot be negative because of the absolute scale, so that will be T1. Now work done, and we know work done how. Let me add one page. Work done W, work done W will be N C T1 minus Tf. Now for this will be N C, since the temperature is less, so this will be Tf minus T1, T2, sorry, because T1 greater than Tf greater than T2. Now rearranging, Nc will be T1 plus T2 minus 2. That is the answer. So this one is the correct answer. Okay. Okay. Now the last problem of this session is how to calculate the change in entropy for an irreversible process. First option says calculate the change in heat along the irreversible path. Calculate the change in heat along the irreversible path and integrate with the temperature. Okay. We have to construct a reversible path and calculate the delta S. That is reasonable because we have talked about constructing a reversible path in before. Third option is divide the heat change in the process by temperature of the initial state. That is also temperature of the initial state. That is also not possible. And option 4 is we can't calculate it. So since entropy, there are few things. Entropy is state function what we have to do, we have to construct a reversible path and then we can write del Q as TdS, exact form. then integrating to initial, integrating between initial and final state, we can get delta S. So option 2 will, second option will be the correct option. Okay, so this is the end. So this is the end. I will revise what we have learned today. So first we have identify the cyclic processes and the each processes in that cycle for Stirling engine, and we came to know there are different kind of Stirling engine. Also, like the in current research scenario, there are different kind of Stirling engines has been implemented using different kind of systems, and then we got to know from TS curve how to find PV curve for any cyclic process. Again, we have found the temperature of hot and cold reservoir if the information between the work and the work extracted and the extracted heat from the hot reservoir is given, but their ratios is given. And then also we from PV diagram for any Carnot cycle, we actually got to know that isothermal processes that in changing internal energy is 0, because for ideal gas is only function of T. Since in isothermal process the temperature is constant, so delta U will be 0. Then in the fifth problem we got to know about the change in entropy for different processes for ideal gases, where here it is done, the temperature is being increased to 4 times of the initial temperature, and the volume is being compressed to 1/4 of the initial volume. Then again we got the basic concept for calculating the entropy, and we got to know that for an adiabatic irreversible expansion, the delta C system is always, let me this is be the correct option. So, and we got to know that delta S system greater than 0, and since no heat exchange to the surroundings, delta S is equal to 0. So the universe, change in entropy of the universe will be greater than 0. And we got to know the basic concepts, and also like same problem from efficiency or for some the temperature of the cold and hot reservoirs, we got to know the heat thrown away to the cold sink. And also like if two kind of same materials bring to the same temperature, thermal contact, what will be the change in entropy. And for an irreversible process, how we can calculate the entropy and different things. And we know also like for reversible engine, the any efficiency is maximum, and for any lesser efficient energy, the engine must be irreversible engine. And from TS diagram we got to know about how to construct TS diagram, and also some problems in this. And also like how to calculate entropy from for irreversible process from reconstructing reversible path. Okay, so this is this. Any question from you guys? I cannot see any question. So if not, then let me stop the video.